All right. I'm happy to see so many people here on a Friday afternoon. And you had 70 chances to see us earlier in the week, so I'm hoping I'm not the first time you're hearing about Discover AQ, but I'm glad that you stuck around for this. You see my name, you see Ken Pickering, my project scientist, and a lot of other names. These are the primary co-investigators on the project, but many, many other people were involved in the project. And down at the bottom, you see our URL, and I want to point out that all of the data that you'll see today is in the public domain, and the data from our last deployment to Colorado will also be publicly available early next year. So this data, we're hoping, is proving not just valuable to our own analysis, but we invite others to join us. I'd also like to remind folks that in doing these air quality campaigns, working with the local air quality agencies, working with the federal agencies and the local universities has been absolutely critical to our attempts to improve the ways that satellites can observe air quality. And so I want to begin by just talking about the investigation very quickly, and hopefully you know a little bit about it already. And the easiest way to do that is start by just using the acronym, which stands for Deriving Information on Surface Conditions, which is that piece of information you want to get from space that a regulator is interested in, what's happening down here at ground level where people are being exposed. But we have to derive that surface condition from a column piece of information, and we just had this past talk about that, and we're going to talk a lot more about that. So that column piece of information from space, and a vertically resolved piece of information, which is an aircraft piece of information, that piece that we rarely get, but in this project we're trying to provide routine full chemical soundings or compositional soundings of the atmosphere in areas where we need observations relevant to air quality. This project began 5 years ago, and so I'm happy to come here today with all of the deployments completed and a chance to show you from a high level. A lot of the things you saw earlier this week were in the details, but I'm going to show you from a high level why I think this project was worthwhile and why I think it's going to feed greatly into the success of these future satellites. When we started this project, we were trying to inform the process of getting GeoCape defined, but in the years that happened afterwards with the acceptance of the Tempo proposal and GEMS and Sentinel-4, it really raised our excitement about what we think we can do with these observations in terms of preparing for what we're going to have to do in the future. Our objectives were to try to relate observations from the column perspective and the surface perspective for both aerosols and key trace gases. Ray Hoff gave a great talk just 2 days ago on the aerosol perspective. Given the time constraints today, I'm going to stick with the trace gases, ozone, NO2, and formaldehyde. And what I'm also going to stick to is the idea of what's happening diurnally. The whole idea behind geostationary satellites will be the fact that we'll finally start to get temporally resolved information from early in the day until late in the afternoon, and what can we expect those satellites to have to contend with, but also I think some things that are exciting in terms of what they may be able to teach us based on what we're already seeing. Very quickly, I want to give you the deployment strategy, which describes how we're trying to take observations. And the key thing is that we've got to observe the atmosphere concurrently in a number of different ways. You see the A-Train satellite system up above, but remember, they only give you a very brief view in the early afternoon of what's going on globally. So we add to that a high-flying King Air aircraft that has a remote sensing perspective. It represents a satellite analog, so by looking with a LiDAR at the aerosols and a UV spectrometer at trace gas columns, we can represent a space-based view all day long. Next, you have the NASA P3, which is spiraling repeatedly or repetitively all day long. We do 3 circuits with 3 spirals over 6 locations throughout the day, gathering in situ profiles of the relevant trace gases and a lot of other things, which unfortunately I won't talk about today, but contextual things that will help us to explain what sources are operative and how the resulting distribution of the things we would see from space are being affected. And then finally, we have ground sites. And at the ground sites, we build it around the regulatory network, so we're spiraling over locations where EPA and state and local agencies are actually making measurements, but we add a lot of measurements on the ground. And one of those perspectives is a remote sensing perspective with Pandora UV spectrometers looking at trace gas columns and Aeronet sun photometers. Today, I'll specifically use the Pandora data, I'll use the P3 in situ aircraft data, and I will use ground-based observations to try to tie together this perspective of what's happening aloft versus what's happening on the ground at any one time. But before I want to do that, I want to remind folks of what our mental picture was of what we would expect before we ever did this campaign. And so I start with, let me show you the deployment locations first. We needed to do this in multiple locations. Here you can see that strategy being laid out in Maryland back in July of 2011. It's been quite a while since we did that. In Houston in September of 2013. California, which is our one wintertime study, focused on PM in 2013, and finally Colorado just this past fall in July and August of 2014. But this picture that I want to paint for you is, what did we think we would see before we went out and did the campaign? And here you're looking at a figure that was actually used in the proposal. It was published in BAMS in 2008 by Jack Fishman and co-authors. And the qualitative picture here that I would paint for you, all this comes from the CMAQ model itself, is that during daylight hours, you're going to see a slight shift between what the column is doing, which you see in blue, and what the surface values are doing, which you see in pink, where emissions are increasing in the morning with traffic. And then as the boundary layer begins to grow, you're going to see the surface values being diluted, and the column will continue to grow as emissions continue. But you will also see, due to chemistry and transport, a decrease in both the surface value and the column value. And Jack was trying to show here that the A-train overpass time is actually, in terms of this particular study, at a minimum for the NO2 column. There are differences from day to day, but that pattern was one that we had anticipated we might see. There's also another view that was published in 2008 by Folker Boersma and colleagues, trying to understand the difference between the morning ski and the afternoon OMI NO2 columns. And here I like this figure because it begins to also point out from a model perspective why the column is changing between the partitioning of NOx from NO2 and NO in terms of the photochemical loss, which is peaking in the middle of the day, and the emissions, which are a little more constant but clearly show a morning peak. And here you're seeing differences. These are normalized for an area that would expect to be influenced by fossil fuel emissions, and you're seeing differences of maybe a factor of 2 throughout the day that would be happening in an NO2 column behavior. So what I'm going to do is I'm going to go from here and I'm going to start showing you NO2 column behavior that we actually saw through the campaigns. And we'll start with Pandora statistics from Maryland. So this is a sun-looking UV spectrometer measuring the NO2 total column. And so the stratospheric column puts a bias in here of about 0.1 on the scale there. And the diurnal variation from the stratosphere should be down around 0.03. But most of you are used to thinking in terms of molecules per centimeter squared. So you see there I've got 1 times 10 to the 15 equals 0.037 Dobson units. That's the precision that we expect tempo to have. And so the precision of tempo is about 1/3 of a tick between each of my major tick marks there. So what you begin to see is that for Maryland, there's no discernible difference in NO2 column within the tempo precision for a given location. There's clearly spatial differences that you're going to expect to see, but it's surprising to us in the initial look that there's really no diurnal trend in the NO2 column. I'm not here to explain that to you today. That's something that the team will continue to work on, but it implies that emissions and chemistry are in balance in keeping the NO2 column constant throughout the day. But what did the aircraft see? And here what I've tried to do is show the profiles taken from the air in the, throughout the day. So 6 to 9 a.m., 9 to 12, 12 to 3, and then 3 to 6. And what you see is the blue line is showing you that things are capped very close to the surface early in the day. The dashed line is showing you the connection between the lowest the aircraft flew and the ground-based data. And so the average value at the ground in the morning was about 8,000, so it's way off that scale. And as the day goes on, you start mixing the NO2 deeper and deeper in the atmosphere. And the value of this kind of information is reminding us that if you don't have a changing a priori, you could begin to infer trends from the retrieval that really aren't there. So the need to have a time varying a priori is going to be absolutely critical to try to do good retrievals from tempo. I'm going to show you here Houston, and again we see very, very flat diurnal trends. In some of the outlying areas like Galveston, which is the blue points at the bottom, you see almost no trend ever. Once you get into town, the yellow points and the light blue points from Moody Tower and West Houston, you start to see some interesting things going on, but in terms of the precision of tempo, not a lot happening in terms of the diurnal change in NO2. It's not all that way, though. I want to paint a picture that maybe is a little more promising. This is the wintertime in California. Now what you're seeing is that in Bakersfield and Fresno, the two cities in the Central Valley, we're seeing factors of 2 to 3 growth in the NO2 column, while the outlying areas, again, show that flat trend that we've been talking about. And when I go to the profiles for the Central Valley, you begin to see that it again corroborates what we're seeing in the columns. You don't see a big change in the surface level of NO2, but you see increasingly larger amounts of NO2 being accumulated and mixed upward in the boundary layer over the Central Valley. So the corroboration between the two perspectives is what was really valuable here in terms of not just seeing what the Pandora is doing, but understanding why it's doing what it's doing. I'm going to throw in here real quickly the standard deviation to remind you that these are aggregated statistics. The day-to-day variability is still quite important to understand, and so I don't want to give the idea that this is a really well-behaved system. It is not. When you look at the columns out over the rest of the valley, you see again a drop in the surface levels of NO2 and a little bit of a gain at altitude, but largely a static column amount. And so this is something that we really didn't anticipate. When we get to Colorado, now we're starting to see some of the highest column densities that we've seen. But they're only in the city, and so those purple points from La Casa is in the middle of Denver. The lower points are from the outlying areas, but even in the lower points you can see some interesting similar trends in the daily profile, but this is a shape that we haven't seen yet. And frankly, I'll be honest, when I saw it, I didn't believe it because this is very recent data that's still preliminary. But there was another site in town at a roadside location where the EPA wanted to understand near-road exposures at I-25. And so when I add I-25, you see that indeed the points in Denver proper have this very interesting diurnal, two-modal trends. If I take away the data down at the bottom and just try to show you what's happening at 3 sites, what you can see is that the ground-based data at these sites shows a very rapid decline, and I would even point out the purple line, which is dropping like a rock, while the purple column points are rising, and that implies that the boundary layer growth has to be extremely vigorous so that you can continue to increase the column because there are more emissions, because the ground-based value to come down by what looks like to be a factor of 3 or 2.5 to 3 during that same time period. So all of these profiles are beginning to show us the diversity in what's happening at different locations. It implies that having Pandoras on the ground in the future would be a great way to keep the satellite honest in terms of should I see a diurnal trend or should I not see a diurnal trend in NO2, and then try to understand that more broadly using the satellite. From here I want to transition though and talk a little bit about the other thing that we're measuring for space, and that's the formaldehyde. And is it going to be useful? If NO2 is not changing during the day, can I use formaldehyde in a way that's going to be instructive? And here I'm showing you more detailed data. So this shows you in the orange data over a 4-day period. It's all the data from the campaign, and then the black lines are the individual profiles on each individual day. So this is 26 to 29 July. The red dashed line kind of helps your eye see that the boundary layer is growing over these 4 days, so it's getting warmer. The formaldehyde column is increasing because you're beginning to energize the biogenics. You're getting a lot more formaldehyde column. The NO2 really doesn't show a pattern. It's not the same every day, but it doesn't show a pattern in time. And then the ozone has different shapes in terms of its profile, but you can see that the ozone is increasing over this 4-day period. So I have 59 individual profiles that I can integrate from the aircraft in situ data, the ozone and the formaldehyde columns. And this is how they compare to each other. And so what you're seeing here is that there's an extremely tight correlation over this 4-day period between increases in formaldehyde and increases in ozone. And in my mind, the reason I'm excited about this is because from our last talk, you saw that we're actually looking at ways to multispectrally see that ozone, but it would be great to have other corroborating information to help us understand that, yes, what we're seeing with the retrieval is being borne out in terms of what's happening in the atmosphere. And so I'm showing you the tempo anticipated sensitivity for formaldehyde, which actually starts to eat into that dynamic range. But with formaldehyde in a sort of regional perspective, I think you could aggregate pixels and start to beat that down a little bit and really begin to see regionally how increases in formaldehyde are going into ozone production. I've also had a chance to add all of the data from the first 3 campaigns, and you see a little blob of green down there. There's not much photochemistry in California in the wintertime, but the other 2 campaigns are showing what is an encouraging, but I wouldn't say perfect, correlation between columns of formaldehyde and columns of ozone. So I'm starting to look into trying to explain what might cause problems with that relationship. And so I'm showing you here Houston on the 25th of September. This was a day that had a very high exceedance of ozone, 120 part per billion at one of the sites over an 8-hour period. So an extreme event. And what I've done here is I've taken the 3 profiles over each location and connected them. And so the points out on the far end are from Deer Park, Texas, which is right near the ship channel. And you can see here that the ozone increased by more than 10 Dobson units, but the formaldehyde really didn't change very much. On this day, things were very stagnant over the ship channel area, and so I'm suspicious that this might be showing me primary emissions of formaldehyde, which really don't represent photochemistry, as well as what you would find in the outlying areas. On the very next day, we had a second exceedance day, but the winds were blowing to the north, kind of flushing out the ship channel emissions. And this is the relationship that I get, where you can see now very nicely the photochemical production of formaldehyde along with the photochemical production of ozone is tying things together very nicely in a way that might show promise for a satellite observation of formaldehyde, which would change by a factor of 5, being able to give us a very small change in ozone, which would be much harder to discern from space. So with that, I'll finish and just say that I believe that the Discover AQ data has unprecedented detail on diurnal trends. I believe that the NO2 columns exhibit some unexpected and diverse diurnal trends that we're going to have to take advantage of. And then finally, I'm hoping that correlations between formaldehyde and ozone will be a suitable proxy with the right additional information on what's happening in terms of ozone production in urban areas. Thank you.
We have time for a very short question. Okay.
I'm sorry? There are upward trends. Let me say it a different way. The column is not showing an upward trend, even though that we know that there are things going on with emissions and chemistry. That's the thing that the models are going to have to go back and explain to us, which is how can you keep NO2 without a trend by balancing all the other factors that are involved in terms of emissions, mixing, chemistry, and other things. In the upper troposphere. Those were total columns, and they should be dominated by what's going on in the boundary layer and lower atmosphere. We don't expect that those trends are being pushed around by upper tropospheric trends in NO2.
Well, thank you very much for this invited